So last what we've done is we talked about sort of the way the iterators were designed, and I talked about two different types of iterators. We had the gang of four style, which is what the undergrads are doing, and we talked about how the nice thing about the gang of four style iterators are that they're relatively easy to implement, but they're a little bit harder to use because you have to keep track of a few other things, like making sure you release the memory. Of course, once you start using auto pointers or unique pointers, that problem sort of goes away because it takes care of itself. But more generally, you have to be aware of allocation of things. It's exposed up to the user. In contrast, the STL form of iterators are harder to implement because you have more things to do. You have to write the various factory methods. You have to be able to think about some of the more subtle issues we're going to talk about when we discuss the prototype pattern shortly. But the good news is it's a heck of a lot easier to use because it's all self-contained. It manages the memory automatically. You don't have to remember to delete anything. It uses value-based semantics, which is almost always easier to keep track of the details than the semantics of pointer or reference-based. Yes, sir?
Is that like what we did when we wrote iterator classes?
Yes, when you wrote iterator classes, so the question was, how does that compare and contrast to the iterator classes that you wrote before? When you wrote the iterator classes for, say, AQ or LQ and so on, you actually wrote STL-style iterators. So you have some experience with it. The main thing is that the iterators that we're doing for traversal of the tree are a little bit more sophisticated than the ones we did for linked lists and the AQ because you have to keep track of subclasses and a few other subtleties. So it's not quite as drop-dead easy. The ones that you did before were tedious, but they weren't hard. They just had to keep track of details. For the grad version, for the STL implementation, for the expression tree, it's a little bit more work. Not impossible, it just takes more thought. That's why the undergrad version just has you do the gang of four style. Okay, so that's where we left off. But the whole point of doing iterators was not just to get access to every element in the tree, although that doesn't hurt. It was to set things up so it would be easy to come along later and add new operations to the tree. That was the real thing we wanted to be able to do. So we used the iterator to get access to each node, but the real end game here was to make it connected with the idea of being able to add an extensible set of operations to manipulate the tree. That's the part that's cool. So we don't want to have to hard code the actions or the operations into the tree itself, but those are things that can be added. And as we had kind of talked about at the very end of the last class, what you have here is this ability to kind of write just a simple piece of code. This looks more or less like regular iterators in STL. In fact, you could actually write this using a range-based for loop if you so chose, because it's so based on the pattern that you can actually automate it using C++11 features. And this is what we're going to use to be able to get access to each element and do something with it. Now, the secret sauce in all this, when we look at this and break it down, is going to be a couple things. First, this is concept of accepting some visitor. So everything's going to have an accept method. That's the single hook, single dependency we have in order to be able to inject new behavior into our expression tree processing. It's this accept method. And then we're also going to be able to provide a visitor, which is going to be the thing that says what we're going to be doing. Now, as you might surmise by looking at the naming of what we're passing into accept for this example, this is a print visitor. But we'll see later we can have other kinds of visitors. And each visitor has to be able to know how to visit a particular type of node in the tree. Now, the magic of this whole thing uses a capability. It's a pattern. In languages like C++ and Java, it's implemented as a pattern. In other languages like C# or certain versions of Lisp, it's actually implemented as a language feature that's called double dispatching or even multi-dispatching. Some languages allow multi-dispatch. C++ and Java do not support multi-dispatch. C# does. And what this allows you to be able to do is it allows you to be able to determine which method to call based on multiple types. And so since these features are not supported as first-class citizens in Java or C++, we're going to have to use a pattern in order to implement this. So the double dispatch pattern is a capability that's used in this broader pattern called the visitor. One of the other things you'll learn as you get more facile with patterns is that patterns often sort of nest and relate to each other. We talked before about bridge composite, where you combine bridge and composite to work together. We talked about pattern sequences, where you're going to have a set of patterns that work together to solve some bigger design problem. Here's a case where a bigger pattern, like the visitor pattern, is implemented in part using a smaller pattern called the double dispatch pattern. We've also seen other examples where patterns sort of depend on each other. We'll see other ones as we go along in other parts. For example, we talked a couple weeks ago about model view controller, which is a pattern that's widely used in a lot of systems, often used for user interface systems. A great example of model view controller, by the way, is Excel. If you take Excel, you can have a matrix with your X and Y cells, and you can associate various visualizations of that matrix using different graphics visualizations, things like a pie chart or a histogram or a box and whiskers chart or whatnot. And you can actually have multiple of those views, that's the view part, connected to the data, which is the subject or the model part. And then as you make changes into the contents of the data, which is through the controller, the views will automatically get updated. And it turns out that the model view controller pattern is implemented in part using the observer pattern. So the observer pattern we've talked about before, that's in the Gang of Four book, is actually a piece of the model view controller pattern. And we'll see lots and lots of other examples too. If you take CS282 next fall, which you should consider doing, several people have already contacted me about that, by the way. If you want to take it, just send me email and I'll get the registrar, Brenda Jordan, to give you the code to override the default. You have to take 281 in theory, but it's not really required. If you take that class, we'll talk about something called the monitor object pattern, which uses something called guarded suspension as a piece of it. So the point there is that patterns are often built up of other smaller patterns. So in this particular case, the accept method is the secret sauce that's going to allow us to be able to dispatch the appropriate visitor in the appropriate way on the appropriate method. And we'll see how it all works. And it's going to use a pair of virtual methods and one non-virtual method using overloading. Yes, Danny?
Is there any reason why when you call the accept function, you don't use the arrow instead of the dereference and then dot operator?
No, we could do it we could do it both ways. Okay, the trick here, again, we'll talk about this more. I'm just going to get you acclimated to the funky vocabulary. This call here is called static polymorphism, which just seems like kind of almost an oxymoron. What it's doing is it's selecting which visit method to call based on the concrete type of the subclass of component node. And we'll come back and look at that later in more detail. But that's one of the things that makes this all work very cleanly. Lawrence?
Is that kind of like in Java where you can call class methods to find out what kind of class you're operating on? And then
Are you talking about reflection? There's a capability in Java where you can ask questions about the classes and objects you have. Yeah, so this is a little different from that. This is a super duper lightweight form of reflection that's built into the compiler to do function and operator overloading. And the compiler, in some sense, is reflecting on the type, although the runtime reflection stuff you're talking about is much more powerful and also much more expensive in terms of runtime overhead. But it's along the same lines. It's in the same family of techniques for being able to decide what to do based on the type of an operation, either statically or dynamically. Yes?
So when we're passing in V, that's a specific visitor pattern that we're passing in?
Ah, great question. So we'll see this in a minute. It'll all become clear. I'm just giving you the overture, if you will. So visitor is a base class, and we're going to have different kinds of subclasses. Print visitor, evaluation visitor, semantic analysis visitor, code generator visitor, all kinds of different visitors. The visitor subclasses are what are actually going to define the actual behavior that we're trying to achieve. That's where the actions or the operations come from. The accept method, which is a virtual method, takes a reference to a base class of visitor. So when you call this thing up here, when you say, let me just step back 1 second, go back up here. When you assume up here there's a print visitor defined. We'll look at that in a second. When I say accept print visitor on this element in the tree, remember the iterator gives you back an element one at a time. When I say accept is a virtual method call. And in this particular case, just for kicks, let's assume it's accepting on a leaf node, the number 4, right? So when accept is called, it's actually going to get dispatched to the leaf node's accept method because it's a dynamically bound call. That accept method here is the one that's getting called there. It passes in a visitor as a base class, as a reference. And so when we say v.visit, this is going to dynamically dispatch the visit method on the visitor object, which of course is also a subclass instance, which is what we get passed in there. So this is a dynamic call. This is a dynamic call. And it knows which visit method to call here based on the actual type of this, which in this case is a leaf node. So it's dynamic binding, static binding using overloading. So it's those three things coming together that makes this all work. Now, that may or may not have made a whole lot of sense. If it didn't make any sense, don't worry. We're going to cover it in more detail. But I'm introducing this one step at a time because people have a tendency to think that the visitor is the most complicated gang of four pattern. And it's by no means easy, but it's actually not that hard if you break it down. It's like so many other things in life, like Latin dancing or something. If you break it down to individual steps, it makes a lot more sense than if you try to do it all in one gulp. Yeah?
So do you need to define a visit method for each kind
Yes.
of component?
Yes. As we'll see in a second, you have a visit method for each different type in the hierarchy. And that's another thing that makes this pattern complicated, is you have two hierarchies that are co-evolving together. You have the visit interface, and then which has a method for everything in the composite that you're going to be visiting. Danny?
So the compiler will be able to tell whether the iterator is pointing to a leaf node or a tree node or something like that.
Yes. And the question is, how does the compiler know which thing? Because it knows it's in the context of a leaf node. So it knows that star this is the leaf node star this. So it can resolve the right visit method to select based on static information. In other words, compile time information. Yeah. No, go ahead.
The dynamic part is that it's able to figure out that it's a leaf node or an iterator pointing to a leaf node. Is that correct?
Dynamically, it figures out that it's so when you made the accept call here, just to make things even more interesting, this is actually a call through the bridge interface, which is non-static. Under the hood, that follows the bridge to the ref counter, reference counter guy that goes to the component node. So you're really calling the accept method on the component node. That dynamic dispatch, and again, we'll break this down in a second, that dynamic dispatch ends up knowing to call leaf node. And then leaf node turns around. This is the double dispatch, right? We dispatch once to get here, then we double dispatch to go find the right visitor subclass. So this call finds the right subclass, or this call with the forwarding operation through the bridge pattern finds the appropriate component node subclass. This call finds the appropriate visitor subclass, and then it picks the right method based on the static type information. And that's why people think this is complicated. Yes?
Since visit is static, did you say it's overloaded? Like the visit method is?
Visit is overloaded. It's not a static method. It's overloaded, so the compiler can decide which one to choose statically at compile time, as opposed to dynamically at runtime. Yes?
And so every item in the composite is going to have an accept function like this?
Every item in the composite has an accept function. Every subclass has an accept method, and every accept method looks exactly the same, except
This is going to be a different type.
exactly. Yes, that's right. Yeah. Tommy, did you have a question?
Yeah, well, I was just wondering, why do we use the accept method instead of just using the visit?
Because it's good question. So it's the double dispatch that's the secret sauce here. So this accept method is getting us to the right leaf node or to the right composite subclass. This accept method is getting us to the right visitor. So it's those two things used together. Now, if this was C#, in C# you can actually do that in one call. You can make a method call and you can pass in two objects, and the compiler will use both objects to figure out which method to call. So they actually bake in what's called multi-dispatch into C#. There are other languages that do that too. But Java and C++, at this point at least, don't support multi-dispatch. OK, now let's take a step back. Now that we've discussed the thing in its full-blown glory, let's break it down step by step so it actually makes sense. So here's the visitor class interface. And it's kind of what we alluded to before, as you brought up, for every subclass for every interesting subclass in the composite hierarchy. Remember, the composite hierarchy is the hierarchy of things that are like, component node, add composite node, or composite add node, composite delete node, composite binary node, composite negate node, leaf node, all those things. Those are all subclasses of component node. That's the composite hierarchy. For every interesting node in the composite hierarchy, we have a method in the visitor interface called visit that takes a reference to one of the things in the composite hierarchy. So what we're really saying here is for everything that's in the composite hierarchy, we know how to do something to it. We're not going to say what we're going to do, because that isn't the job of the base class. the visitor base class. That's the job of a visitor subclass. We're just saying somebody will know what to do for each of these different kinds of things in the composite hierarchy. So that's what the visit class is all about. So we have an overloaded visit method for each component node subclass, or more generally for each thing that's in the composite. Yes, Mitchell?
Visitor pattern kind of uses bridge pattern.
That's an interesting question. In my mind, they're distinct patterns. In this particular case, we happen to be using them somewhat together. What you're really able to do with, actually, visitor pattern is more like the strategy pattern. Now, having said that, strategy and bridge have a lot in common too, as we'll see a little bit later. But let's use strategy. So strategy says, I'm going to give you an interface, but I'm not going to tell you how it's going to be implemented. And, oh, by the way, there are going to be multiple different ways to implement this thing. So what visitor does is it takes that one step further. It says there's a bunch of different things that can be operated on, and I'm going to define visit methods for each one of those kinds of things. And then I'm going to be able to sort of define wholesale a bunch of different strategies for each of those different things. So visitor, in a sense, is kind of like strategy working on a composite. That's one way to think about it. It's not the only way to think about it, but it's one way to think about it. And it's a good observation. You're along the right tracks because they seem similar to each other. The difference is strategy typically gives you a way of doing things one at a time, whereas visitor gives you a way to do a bunch of things together that work on some composite entity or structure. Yes?
So I see that we're kind of interacting with different kind of nodes as in like addition and subtraction.
Yep.
Couldn't we treat all the nodes as kind of the same and use like a stack and kind of read off of that?
Yeah, great question. So what you could do in this case is you could kind of collapse this into something that's called visit component node or composite node or something like that, which would mean you'd have less methods. But then at runtime, you would have to go and do a runtime type identification to figure out which kind of thing you actually had. So you can narrow the interface at the expense of more runtime overhead to look things up dynamically, A, and potentially less type safety because you may miss a case at runtime as you extend and modify your program. But you're right, you could do that, in which case it becomes a bit more like the strategy pattern. So here's how we have commonality and variability. Commonality, we have a common accept method for all expression tree nodes and a common visit method for all visitor subclasses. And here's the variability part. You can have a base class like the visitor, which is what we see here, and then you can subclass it to make different kinds of visitors. Each subclass defines a group of operations that perform some defined action on the composite structure that we're operating on. And this is how we're going to be able to add new actions, add new operations, add new behavior, and so on, without modifying anything in the structure. They're not coupled. They're only connected through the accept and visit methods. Yes?
So our accept method is figuring out which type of node we're operating on, and then the visitor helps, or visit picks which visitor pattern.
Visitor implementation. That's exactly right. So accept is figuring out which concrete node, just using dynamic binding. Visit is figuring out which concrete visitor. So those two things put together get you double dispatching to get the right visit method, the right method invoked on the right visitor for the right node. And then we use static polymorphism with function overloading, not operator overloading, function overloading, in order to pick the right method. And you'll see that a little bit more when we get a little further along. Yeah, that's a really good way to look at it. OK, so the way of doing all this stuff, which, by the way, is mystifying to most people, is called the visitor pattern. I'll never forget I was at a conference many, many years ago, and this is 1997, 98 time frame. The Gang of Four book was out. It achieved instant cult status maybe a generation or two before. Donald Knuth's famous books on algorithms had the same effect. Everybody would go and buy those books and put them on their bookshelf. Didn't always read them, but when you went into their office, you'd see a book that was like Donald Knuth's book. You'd be like, oh, this person's really cool because they have Donald Knuth's book. Well, the Gang of Four book was kind of the same way. So I went to a conference one day, and some guy got up, really great speaker, and his name is Robert Martin, or Bob Martin, really interesting guy. And he said, how many people here have heard of the Gang of Four? And everybody raised their hand. And how many people here have got the Gang of Four book? And 99% of the people raised their hand. How many people here have read the Gang of Four book? 50% of the people raised their hand. How many people here understand the visitor pattern? And 2 people raised their hand. So, so there's a clear, there's this funnel effect going on from having access to the source of knowledge and actually exposing yourself and understanding knowledge. And there's a lot of different degrees of understanding in between those things. So the intent of the visitor pattern is to centralize operations on an object structure, like a composite, so they can vary independently. You can change them, but they can still behave polymorphically. In other words, you can select at runtime. You could dynamically modify what gets done. Quite frankly, that still doesn't give you a lot of information about what this thing is about, right? That's the intent. If you read the Gang of Four book, that's what it says, but it's not entirely clear what that means. Here are some situations under which you might want to use this. When a class defines many unrelated operations, so printing, evaluation, semantic analysis, code generation, those operations don't really have much to do with each other. They all work off of a common structure, the tree, but they don't really have a whole lot to do with each other, right? When the class relationships in the structure rarely change, this is really important, but the operations on them change relatively frequently. So the best way to think about this is to look at a picture. So here's an object structure, right? Here's an object structure. And the idea is, imagine our composite structure here. The elements in the composite structure don't change a whole lot. So you've got things like add nodes and subtract nodes and multiply nodes and divide nodes, leaf nodes. Those things aren't going to change a whole lot. You might add a new node once in a blue moon, but it's not an everyday thing. So this is fairly stable. But the operations that you want to do, the things that you actually do to those nodes, that may want to change. You may have new things. You want to add new capabilities to your structure. That's what this hierarchy is for. This is the operation or action hierarchy. This is the object structure hierarchy. And the other reason you might want to use this stuff is if the algorithms that you're running to manipulate the elements in your object structure need to keep state that's modified as the traversal is taking place. Now, for something really simple like printing, there's really no need to keep state. For something more interesting like evaluating the tree or doing semantic analysis of the tree or doing code generation from the tree, undoubtedly you'll need to keep some state to do optimizations and keep track of the running total of what you're evaluating, et cetera, et cetera. So you want to be able to keep that information not in the tree, but instead in the visitor.
When you say that behaves polymorphically, do you mean like it's able to maintain a common interface between all these?
So it means a variety of things in this context. So we have, as I mentioned, we have 3 different things that are polymorphic, 2 of which are dynamically polymorphic, 1 of which is statically polymorphic. So really what we're saying here is we want to be able to make changes to stuff. We want to be able to add new things. We want to be able to add new operations. Maybe we want to be able to add new types of nodes and so on. And we want to be able to do that in a way that as much as possible doesn't affect the overall architecture of the framework we have to do this. So polymorphic just means making decisions at runtime or even at compile time where you have something that supports many variations in a clean, uniform way. Yes?
By static polymorphism, do you mean like type overloading?
Function overloading, operator overloading. In this case, it's function overloading or method overloading. Yeah, that's just a fancy name. Static polymorphism is a fancy name for function overloading. OK, so let's take a look in a bit more detail. In terms of the program you're going to be implementing, the visitor is the expression tree visitor. I think your thing is just called visitor in your shell files. But if you're building a bigger system, you'd want to qualify the name to make it more legible, more unique. We have different kinds of subclasses of visitor: evaluation visitor, print visitor, semantic analysis visitor, and so on and so forth. The element hierarchy is rooted at component node. And then we have a bunch of different types of nodes, concrete elements as they call them in the pattern. So composite add node, composite binary node, composite unary node. These are all things you're going to start getting into in assignment 4D very soon, if you haven't taken a look at it already. So what's so cool about this, of course, is how nicely the elements in the pattern map onto the elements of the software we're doing. And as you start getting more familiar with patterns, this is a very common thing. You'll start finding yourself really getting comfortable with using the patterns to guide your designs, using the patterns to help document and rationalize and guide the way in which the implementation will unfold. But like in so many things in life, it's not always clear to everybody, me included, what UML diagrams mean. So here's some code for those of you who like code. So here's a print visitor. As you can see, print visitor is a visitor. So it inherits, in this case, publicly from visitor. And it defines a whole bunch of visit methods, one for every element in the composite. So for every component node subclass, there'll be a visit method. And then we can combine this thing with any traversal algorithm. So here's a case where we have a print visitor, and we've got some kind of factory called make visitor. We could do this a variety of different ways. And we say, make me a print visitor. And what we get back is we get a print visitor back here. And then in this particular case, what we're going to do is we're going to traverse through the tree in some order. It's post order, pre-order, in order, it doesn't matter, level order, whatever the order is. And for every node in the tree, we're going to ask that node, please accept the print visitor and double dispatch with this thing. Okay, so that's the overall flow of here. We make ourselves a particular kind of visitor. Now, in real life, you'll see there's some subtleties here, but this is the basic approach we're going to be doing. Any questions about that? So what's taking place under the hood, of course, is when the accept method is called here. This is the bridge pattern. And so it'll be calling the accept method through the abstraction interface. This doesn't have to be a dynamically bound thing. Under the hood, that will follow to the implementation object that's part of the abstraction through a pointer or a ref counter in your implementation. And it follows that, and it delegates to its accept method. It forwards to it, which, of course, is going to be the accept method that's from one of the subclasses of component nodes. So it'll be a leaf node or a composite add node or a composite delete node or whatnot. And that guy will end up calling visit on him or herself, and then that'll cause the right behavior to take place. So that's one view. That's one way of looking at this. Let's take a different way to understand the interactions between these things. One of the great things you'll discover as you start getting more into software design is that people who've done this for a while have tried to come up with notations that are relatively straightforward and relatively unambiguous to characterize how to understand what your program's doing without having to sit there and walk through the compiler or debugger or something like that. So let's take a look at an example. We're going to see here just a snippet of the code here where we're going to have an iterator, a leaf node, a composite negate node, and a print visitor. Those are the four elements we're going to use. And we're going to demonstrate how those elements interact with each other using an a UML sequence diagram. So you see here we have the iterator. That's basically what we're showing over here. We're iterating through each element. And so we say go ahead and accept the print visitor. And that ends up being called on the leaf node. Now keep in mind, that's a virtual method being dispatched through something that looks like a pointer to a component node, but in fact it's delegating to leaf node because we happen to have a leaf node in this case. That leaf node then says, visitor, please come visit me. Now in this particular case, visiting a leaf node is something a visitor knows how to do, because if you take a look earlier, you'll see that leaf node is one of the methods that's defined on a visitor, right? So it knows how to visit one of those things. So the print visitor will say, OK, I know what to do when someone wants me to visit a composite leaf node. I know how to do that. And or actually, it's not a composite. It's actually the one at the edge. It's the leaf node. It goes ahead and it calls the visit method. And what the visit method does is print out the item, because that's what you do when you're visiting a leaf node. It's just going to print it out as whatever value it is. In this case, it would be 5, for example. Then, as we're parsing through the tree, let's say that we're going through this in the appropriate order. And then it's going to go ahead and accept the print visitor again on the composite negate node. That's going to say, come ahead and visit me. And what that's going to do is when you visit something that's a composite negate node, it's a little hard to see this. This is supposed to be unary minus. Looks more like a period. It goes ahead and visits the composite negate node, which prints out the minus sign. So that's what it means to visit that kind of operation.
So does negate node not have a dot item that is minus?
Keep in mind what the tree looks like. Let me step you back. Here's a picture of the tree. So we were iterating through this part of the thing, right? And let's say we were going in post order. So we're going to print this guy followed by that guy. So this particular sequence will first, the iterator will first go to this node, which is the leaf node. It prints that out, prints out 5. it then goes and visits this node, and it prints out the minus.
I'm just curious as to why for the leaf node it was just C out this dot item.
Oh, because that's item, in our particular implementation, item returns the value. You could also overload item to return plus or minus or whatever. You could do that too. It just gets confusing. Okay, so that's a little, yeah, Danny.
So print visitor is supposed to be able to implement these actions. Why is it, and we had a code snippet of earlier, why does it have this visit function declared virtual?
The reason you need the visit function declared virtual is because you're going to subclass from visitor in order to change the kinds of actions that are performed wholesale. So we're going to have a print visitor, an evaluation visitor. And if you use virtual functions and inheritance in order to be able to change what the visit method does.
Print visitor provides limitations for these, like the actual
Yes.
stuff. Okay.
So print visitor, if you take a look back here at print visitor is a visitor.
Okay.
So it overrides those methods and fills in what they need to do.
Then it just declared virtual because it was declared virtual in the ET visitor.
That's correct. Yep. Yeah. That's for that particular question, that's just good old object-oriented programming, straightforward stuff. Yes?
I was just confused about why the print visitor is an object of the visitor class and not the print visitor class.
So, okay, so let's take a look here. By the way, there's a couple different ways. So your question is, why doesn't this say print visitor, right? Okay. Anybody want to take a shot at that?
Is it just more generic since you have all the functions defined? It kind of just knows what type it is and what call it is.
In fact, to make that even more clear, let's do this. So the cool part about this, now you'll see later that it doesn't quite work this way quite so easily, but in theory it's basically the idea. Remember, I'll go back and show you something back here. There we go. So here is a picture that illustrated visitor is a base class, right? So that means it has some things in common. It's got a bunch of virtual methods. It's got visit for all the different kinds of composite nodes and other kinds of component nodes. Evaluation visitor is one subclass. Print visitor is another subclass. Whenever you have something that's a subclass of a base class, then you can make an instance of the subclass, and you can always pass a pointer or reference to that instance to a pointer or reference to an instance of the base, or use it in the context to the instance of a base class. So visitor is the base class. So print visitor, evaluation visitor, semantic generation visitor, whatever, those things are subclasses. So we can make those things in our make visitor factory, and they can all be treated generically as visitors. And that, I think that was part of what Danny was asking before. That's really the essence of object-oriented programming. That's 101, right? Inheritance hierarchies, you can use a pointer or reference to a subclass anywhere you expect a pointer or reference to a base class. So it's more generic. At least in theory, we could come along and change make visitor to make evaluation visitor, or make a semantic analysis visitor, or make a code generator visitor or whatnot. And that code would remain more or less the same, just push the behavior into the factory for making the right kind of visitor.
Even if you declared this visitor as just a visitor, not a print visitor, or anything
Uh-huh.
along those lines, then how is the compiler able to determine then the correct sort of the set method to call this?
Oh, great question. All right, so the question is, and let's assume for the sake of argument that we're not using fancy bridge pattern stuff here. This is just, let's assume that we're getting back something that is in fact a component node here, right? So auto is getting it back, iterator is of type component node pointer, or something like that. So we're going to say, component node pointer dot accept, where this is a reference or a pointer, accept. This obviously is a base class. This obviously is a base class. How is it that the compiler knows the appropriate accept method to dispatch in that case? What's the magic in C++ and Java that's used to dispatch things dynamically?
The vtable.
The vtable, right. So there's a virtual table. Every subclass has a virtual table. that defines the set of operations, the set of methods that are available for that particular table, for that particular class, that have been overridden as virtual functions. And every object that has virtual functions in it also contains something else special. What's that called? The V. V pointer. So every object has a V pointer, virtual pointer. The virtual pointer, every object that has virtual functions, not every object with virtual functions, has a virtual pointer, and it points off to the appropriate virtual table. And if you want more information about this, go back and take a look at the introduction slides in C++, since they're all recorded for posterity. Go back and take a look at the discussion of virtual functions and dynamic binding. And in those examples where I talked about a stack, I think it's, I don't know, section 6 or 7 maybe, I walk through exactly what happens with dynamic binding, where it takes basically the virtual pointer, uses a virtual pointer to find the virtual table, indexes into the virtual table using the function slot number, finds the virtual function, and then calls it. So it's basically doing a dynamic lookup at runtime based on information stashed away by the compiler at compile time.
What class is make visitor a method?
Oh, it's just a factory function, right? It could be a standalone function. If you go back and take a look at one of the driver programs for assignment 4A, you'll see that there's a factory function called makeQ. You pass makeQ a string with the Q you want made, and it gives you back the appropriate subclass of Q. Remember using your Q adapter? This is just the same thing. It's just a factory function that makes you the appropriate visitor.
So our iterator is pointing to a specific node type.
Yes?
And when we dereference it, we have the node type, which is a virtual class. Or it's a class that has a vtable, and it has its own accept method.
So more specifically, let's make this real specific. Let's say that this function gives you back a component node pointer, right? So component node is the root of the hierarchy. Component node has an accept method that's virtual. When you say, star iter accept, that's doing a dynamic dispatch. That's going to take that pointer, find its v pointer, find the appropriate slot in the v table that corresponds to the accept method, index into that vtable slot, find a pointer to a function that implements accept for that appropriate subclass of component node. In this case, maybe a leaf node, for example. Calls that function, passing in this and any parameters. In this case, it's the visitor. So that's how the dynamic dispatch gets done. Again, all that stuff is described in an earlier video where I talked about dynamic binding. So if you want to go back and look at that, take a look. It's important to understand how that works. At the time we discussed it, probably didn't make that much sense because we weren't thinking about it in this kind of detail. But it's good to go back, and yet another benefit of recording stuff. Yes, sir?
We used auto instead of visitor the first time. We should not have visitor.
Okay, so if we replace, that's a really interesting question. So here's what's being recommended. If your goal is to totally and completely confuse the reader, you could say auto. So what's going on there, of course, is the compiler knows the type of visitor in that case, right? What is the type of visitor in that case? Or what is the type in that case? No.
Visitor.
Visitor, yes. It may happen to point to print visitor because of what it's allocating, but it'll be treated by the compiler as visitor. Why is that? Maybe I'd probably have to show you make visitor to see exactly what I'm talking about. But why is it going to be, actually it's going to be a visitor pointer or visitor reference.
Because make visitor returns a visitor pointer.
Make visitor returns a visitor pointer or reference. Why does make visitor return a visitor pointer or reference?
Because accept uses a visitor.
Because we wrote make visitor.
Because we wrote make visitor. I'll tell you what I'm going to do. This is actually something, I have a feeling that, like so many things in life, when you see stuff the first time, it doesn't always make sense because you don't know why you should care. But since everybody's asking these questions, let me go back here and we will kind of walk real briefly through this piece of the code. Okay, so this is a quick recap, greatest hits of week 2 or 3 probably. So remember the stack? We did lots of stack examples. So here was an example of what we called an abstract base class. Hopefully you have a pretty good feeling for that. An abstract base class is just something that doesn't have an implementation. It relies on subclasses to provide the implementation. An abstract base class defines a set of obligations on subclasses to fill in the interface it defines. What's the equivalent in Java to an abstract base class in C++? Interface would be a great example, or just a class that's abstract, right? Same difference. So there actually are some differences. What's the difference? A little Java trivia question for you. What's the difference between an interface and an abstract class in Java?
Interface, you don't implement any of the methods, and abstract base class, you implement some.
Great. So an abstract class in Java, you can, in fact, implement some methods. Likewise, you can actually define data members as part of the abstract class, but for an interface, you can't. Yeah, that's good. So here's the interface, right? That's just saying no implementation at this point. Here, then, is one implementation, right? So we have a V stack that inherits from stack. Later, we also had an L stack. Here is L stack. So L stack inherited from stack. L stack, V stack. 2 implementations that inherit from the interface. And then what I did is I showed you this picture, and I said, if I've got a subclass of stack, like a V stack, which is implemented with a vector, or an L stack that's implemented as a list, I said for every subclass of the base class, every V stack or L stack that inherits from stack, there will be something called a V table. That's what this funky thing is, right here. That's the V stack V table. And there is a V table is just an array that contains some information. One of the information in every slot in the array is the pointer to the actual implementation function. So for example, over here, if you take a look at VStack, there'll be an implementation of push, an implementation of pop, an implementation of top, etc. So push, pop, top. Those are pointers to functions, good old C-style pointers to functions. Every instance of VStack or LStack or whatnot will have the normal elements, right? So here's VStack. It's got a top, and it's got a stack, which is a vector, and so on. So it'll contain those things. In addition, it also contains a V pointer. So this is the V pointer, pointed to a V table. So the V pointer points to the appropriate V table. And then, and this will require skipping ahead a little bit, take a look at the actual example here. If you take a look at a call like this, we're going to call print top, passing in a stack. This is almost identical to what we just looked at, right? So here is make stack. Remember in the other thing we had make visitor, same idea. Make stack returns a pointer to a stack, but it makes either a VStack or an LStack. Those are subclasses. We're making those things. We call make stack. We get back a pointer, and then we go ahead and we say print top, and we pass in the stack pointer. And what this does is this says SP for stack pointer arrow top. So that's identical in terms of implementation to, iterator arrow except, right? Same idea, right? It's calling it through a base class pointer. And what happens under the hood is that this turns into SP arrow V pointer, which is the thing we showed here, V pointer, which takes us to the V table. Sub whatever the number is that corresponds to that method. In top, I guess, is the third one. So push was first, pop was second, top was third, so it's the third one. SP V pointer 3, which is the third one. What's stored there is a pointer to a function, a C-style function. It calls that and passes in this pointer, which in this case is the stack pointer. So that's what dynamic binding is all about, right? So you can see a couple things. You can have an arbitrary number of things you can add and keep refining. The overhead is minimal. It's just a couple of extra indirections. Good compilers will optimize the heck out of this, so it just disappears altogether. So now maybe when we come full circle, you can see a little bit more about what we were talking about before, and now we're using it in the context of our double dispatching for the visitor pattern. Yeah?
So in the V table, does that contain pointers to multiple pushes?
Great question. So let's say for sake of argument that we have two subclasses, vStack and LStack. They both inherit from stack, and they only have one method with a single name in each one. They don't have overloaded pushes or overloaded pops, just to make it simple. So in that particular case, for every virtual method in the stack class, there will be a slot in the vtable. So if push is the first method, it'll be in location 1. If pop is the second method, it'll be in location 2. If top is the third method, it'll be location 3. So every vtable contains the virtual functions that correspond to the subclass's behavior of those functions, the subclass's implementations of those functions. So of course, vStack will have its own set of push and pop methods. The vtable for vStack will have its own set of push and pop methods in top. The vtable for LStack will have its own set. Those will be independent. Where it gets interesting is what happens if we had a base class, which we don't have in this case, but if you had a base class with a virtual method that was not pure virtual, so we had to provide an implementation. What would happen then is the vtable for LStack and the vtable for vStack would have a copy of the same method. So when you inherit something, its pointer simply shows up in your vtable. So you're reusing the implementation. You're just storing a pointer to it in your vtable.
What happens whenever you rewrite a virtual function?
You mean override a virtual function?
Override is the term.
Oh, great question. It's really simple. Whenever you override a virtual function, your vtable gets the overridden version.
So you just change that pointer.
Well, you don't change the pointer. The compiler generates code that puts the pointer in there for you. Exactly. And so in some sense, inheritance, if you take it really literally from an implementation point of view, it's nothing more in C++ and Java that are statically dispatched. It's nothing more than making sure that the functions that go into your vtable correspond to the most derived functions in the inheritance hierarchy. And of course, if you don't override everything, if you inherit some, then those will come from your parents or your ancestors. But you always have the most derived in your vtable. So it's very efficient, very cool, very clean. So hopefully that kind of ties a few loose ends together that maybe weren't so clear before. All right, so popping back here to the stack example, or sorry, to the visitor example. All right, so now that we've completely rewritten this code to be maximally impenetrable for people who don't know C++11, make visitor is like make stack, right? It's going to return a visitor pointer, just like make stack returned a stack pointer. And it's going to return the right kind of subclass. Print visitor, it might return evaluation visitor, or so on and so forth.
We have some visitors.
Yeah, we have visitors. Will we accept them? That's the question. And so the point, the earlier question was, and let me make sure I understood your question and have answered it. So irrespective of whether we put auto here or not, the type is the same. It's just that if we put auto, the compiler has to figure it out on its own, which isn't hard. It's not hard for the compiler. If we put visitor here, then it has to figure it out. It'll do it a slightly different way. Yeah?
If instead of that first line with factory, if you had just called the print visitor, so if you just made a print visitor object, would that still run?
No. I was being, that's the danger of changing your slides on the fly. But so this would work fine, right? When we had before print visitor, that works fine, okay? Because we're making ourselves a visitor. Actually, it would probably have to be, depending on various things, maybe a print visitor pointer or something like that. I'm being a little fast and loose with the pointer stuff. If we change this to visitor, then that's probably got to be like this. Which again is another good reason why I think I'm going to go with auto. Because now I can sweep all those details under the rug. But it would have to be whatever is the right type in that situation. Another question? Yeah?
You said visitor has to hold state if you want to.
It could hold state, yeah.
Would print visitor take care of that?
Print visitor doesn't need to hold state, but the other visitors will do for so for assignment 4C, your print visitor doesn't have to hold state. For your assignment 4D, your visitor does have to hold state because it has to keep track of the expression that you're evaluating as you're evaluating the expression in the tree piece by piece. And so it has to keep track of a stack. It'll use a stack that'll keep track of how far along it is in the sub-expression evaluation process. And you'll see later when we talk about this, it's really easy to do. Okay. So we looked at this, showed how things dispatched. So we looked at print visitor, which was a very simple example. Let's look at one that's a little bit more sophisticated. It's not super more sophisticated. Just as you just pointed out, it's going to actually have to, no problem. It's going to have to go ahead and understand how to keep state. So we're going to have an evaluation visitor. Its purpose in life is to walk through every element in the tree and give the yield of the tree, yield being the value that's computed by the nodes. So here's how it's going to work. We have the same interface. Print visitor had, evaluation visitor has the same interface because it inherits from visitor. The difference is it defines a stack. And what it does is all of its methods will do the appropriate thing, where appropriate thing means pushing or popping elements on the stack. So as you can see, we keep a stack of operands. And as we're iterating through the tree, and we have to make sure we iterate in the proper order. We have to iterate in post order, for example, or reverse pre-order, as we'll see later on. As you're iterating through the tree in the right order, every time you come to a node, the visit method does the right thing. So if we visit this guy, that's going to push the item onto the tree. If we visit this guy, it's going to pop the current item off the stack and negate it and push it back on. Again, these are conceptual push and pops. These are not exception-safe stuff. Your actual code will have to be a little bit more verbose, but I had to fit it onto the lower right-hand corner of the slide so it would fit. So I took a few liberties with semantics of exception handling. So you see a 5, you push it on the stack. You see a negate node, a unary negate node. You pop the value off the stack, which is 5, negate it, push it back on. And this is showing you what's in the stack, right? When we get down here, we're going to go ahead and push 3. We push 4. We see plus. We pop off 3 and 4. We add them together, push them back on. Now we have 7. And then the final thing we do is we pop the left, pop the right, multiply them together, push them back on. And if everything goes according to plan, and your code is correct, and the expression is correct, blah, 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 by the time you're done parsing, the top element should just have the value of the whole tree. So that's how you evaluate the nodes in the tree. Here then is a diagram that illustrates this as a sequence diagram. As you can see, identical in every way. There's just the only difference is the kind of visitor differs, right? Before we had a print visitor, now we have an eval visitor or evaluation visitor. We have an iterator. It gives us each node one at a time. When we get a leaf node, we say, please visit me. And that turns around and pushes the value of the node onto the eval visitor's local data member, which goes back to your question about state. We go and do the next one, which is a composite negate node. We visit it. That goes ahead and pops the item off, negates it, and pushes it back on. So what's cool in all of this is really cool, right? What's cool in all this is think of all the things we're varying and think of all the things we're keeping the same, right? So what are we varying? We're varying the iteration order. We're iterating in a different order. So that's one thing that varies. How do we do that? Well, we simply pass in a different string to begin and end that are the iterator factories. We'll see more about factories later. I think next class maybe talk about factory methods. We pass begin and end, or we pass a traversal order, tree, in order, pre-order, post-order, and so on, into the begin and factory methods. That creates us the iterator. That tells us the order in which things iterate. So once we've got the iteration order, that's fixed. We then iterate using the iterator pattern in the right order. And for everything we're iterating through, we call except on it, which turns out to double dispatch to except is a virtual method that is dispatched to its appropriate subclass, which is one of the elements in the composite, which then double dispatches to the visitor implementation. So be composite visitor, print visitor or eval visitor and so on, evaluation visitor. And then that uses static polymorphism to visit the appropriate node in the right way, be it an add node, a delete node, or add node, divide node, leaf node, etc. So all of those things are kind of baked into the structure of the program. So lots of things are fixed, but some things vary. But the stuff that varies can vary in very, very stylized ways. So it's really easy to keep the code the same and then modify the behavior without really any change to the overall structure you get different behavior out of the same code. Yeah?
So the call to visit this is the double dispatch. That's the double dispatch.
The call to visit this is a double dispatch. This is the first dispatch. So the first dispatch finds you the right composite subclass. And once you've got the right composite subclass, you then say, visitor, come visit me. And that goes ahead and it finds you the right visitor subclass. And then depending on what type the subclass is, that picks the right method to dispatch. So it's still a dynamically dispatched method, but it's selecting which of the dynamically dispatched methods to call using function overloading, which is resolved statically at compile time. That information gets compiled into the code. But the actual, so the selection of the type of method is in the code, in the compiled code. The selection of which object's method is determined dynamically based on the vtable lookups that we talked about.
The eval visitor implementation that you just showed used post-order traversal. Does it change to work with like pre-order traversal?
Yeah, there's a variety of different things that we'll talk about later when we get to that point. So if you're doing post-order traversal of a tree, it's really easy to write an evaluator for that. Likewise, if you do pre-order traversal of a tree, if you take the pre-order traversal of a tree and reverse it, then you can use the same evaluator that you did for post-order traversal. I have absolutely no idea why that is the case. It just turns out that mathematically speaking, you get the same result. You could also, if you were so inclined, write a pre-order evaluator or a level order, or a level order evaluator would be hard. In order might be hard too, but because you have to keep a lot more state to keep track of sub-expressions. But post-order, piece of cake. That's why, by the way, back in the early days of computing, of calculators, people used to use what was called RPN calculators. Do you know what RPN is? Right. RPN is reverse Polish notation, also known as postfix. Pre-order traversal is Polish notation. So reverse Polish notation is basically the inverse of that in some sense. And so it's really easy to write a stack-based machine to compute things that are in reverse Polish notation, which is why all the early calculators were done that way, because it was really easy to write that. Now, most people don't think like that, but if you find somebody who's probably in their 60s or so who was an engineer back in the day, they probably know how to do that really conveniently, because that was the way people did it in those days.
My mom still has her old Hewlett Packard,
Yeah.
which I don't know how to use. It's on her desk, and that's the only calculator she'll use.
It's so funny. It's once you get used to it, it's probably intuitive. But most people today don't think like that. It's just odd.
Was the reason the double dispatch is required as opposed to just like a single method call because with the visitor pattern, we've got the visitor class and we've also got the element class, so they have to implement their own. I guess they have to implement their own data.
So the reason we need to use the visitor pattern and double dispatching as a pattern is because C++ and Java don't support multi-dispatch or double dispatch as language features. Other languages like C# and so on do. And so in that case, it's really simple. You don't need to make a pattern out of it. You just call the methods and it's built into the language. So we have to do it as a pattern, and this is the way to do it as a pattern, to have these two hierarchies that co-evolve and relate to each other. John?
You mentioned callbacks last time.
Yeah.
So which part of this is the callback?
Oh, there's callbacks all over the place. So this is definitely a callback, this being the call to visit. So in this particular case, if you think about what we're doing here, pop up a level. Go see the caller. So, actually, let's go back even farther. Yeah, here we go. So this guy is being passed a method, right, print visitor, and that's showing up here. And then we're going to call back on that parameter we passed in. So that's sort of a callback to that guy. Or it's not a callback in a deep sense of a callback, but it's doing a dispatch. Okay. So let's talk a little bit about this pattern. Some cool things about it. Why do we do it? Actually, where is it ever used? Well, I guess we'll get to known uses in a second, but first we'll talk about some of the good and bad things about it. So consequences. It's very flexible. As long as your object structure doesn't change a lot, you can have new behaviors. Because we're not going to modify the structure, but we can add the new behaviors. It also separates concerns. the real logic, the actions, the operations, and so on are localized in subclasses of visitor. And everything else just kind of comes along for the ride. All that other structure comes to you from other means. Those are the good things. The downside is that it's somewhat tight coupled. There are circular dependencies between the visitor and the element interfaces. This is one reason why we give you the assignment shells. When in the bad old days before we did that, we would have people do this, writing the code themselves, and many students, an alarmingly high number, would get stuck trying to figure out how to break the circular dependencies between the various classes that are related, trees and nodes, or visitors and elements. It was just driving them crazy. So we just give you the shells. Someday you'll have to learn how to do this, but you don't have to do it right now. One of the other consequences because of this tight coupling is it's brittle to new concrete element classes. If you start making changes to your element hierarchy, so the part that's over here, this part right there, oops. Come on. There. This part, if you start making new concrete elements, you're going to have to modify all these methods in visitor and all of its subclasses, because it's got to have a method for every different subclass of the composite. So that is less desirable in situations like that. Double dispatch, go take a look at Wikipedia. It'll explain double dispatch. I think there's some good examples at that link that illustrate other languages where they support double dispatch or multi-dispatch natively in the language, worth taking a look at. What's the interface to the elements of the object structure? Is it narrow? Is it broad? I've given you a very broad interface with lots of overloading. You can also kind of neck it down a little bit and have a narrower interface and do more runtime type dispatching and so on. And lots of uses. The primary place that visitor is used is in compilers and language processing tools, like our expression tree calculator. And the reason for that, of course, is because those types of things tend to have a lot of composite structures. So we talked before about compilers. Compilers typically have a front end and a back end, and they talk to each other through some kind of intermediate representation, like a syntax tree or a parse tree. And once you put things into a tree-like form, the tree nodes typically have different behaviors or semantics associated with them, but they're all part of a common structure or common composite. And once you do that, it's often the case that at some point your input you parsed and analyzed and so on, maybe optimized, is stored in some internal representation that's an expression tree-like format. And then you may want to do stuff to that code. You may want to analyze it. You may want to optimize it. You may want to generate object code for different target programming languages. And Visitor works really, really well to separate out the different kinds of things that you might want to do to a common structure. So that's why it's often used in compiler examples, and that's why you'll see many of the known uses are from the compiler world. There are other cases as well, manipulating complex composite structures for various kinds of rendering, various kinds of graphics, another place where you could use Visitor. It's one of those patterns where it doesn't have that broad of a usage model, but when you need it, it really comes in handy. And so once people understand it, it cleans up a lot of code, although not everybody has that particular set of problems. Okay, any questions about any of that stuff? All right, so I think we're going to stop. Well, we won't stop here. I'm going to give you a preview of what we're going to talk about next. This next discussion is primarily for the grad students taking the class, or anybody who wants to do the grad version of the assignment. And it basically just shows kind of how you have to implement the STL, the expected STL operators like plus plus and minus minus and so on. And we're going to solve some niggling design problems by using something called the prototype pattern, which has this method called clone. And so we'll kind of talk about that. It's a very interesting pattern, has some very powerful use cases. In fact, some programming languages rely on prototype for many, many things. A good example would be JavaScript, which basically doesn't really have classes at all. You use objects as prototypes and you clone them. So we'll talk about that. Let me also give you a little preview of where we're headed with all this stuff. So you can see here of the several hundred slides in this deck, we have slides that will cover the prototype pattern, and then we're going to go ahead and cover a bunch more patterns. We're going to cover commands and factories. Factories are really cool. Use factories a lot. Commands are also pretty cool. For my money, I actually don't think that the visitor pattern is the most complicated pattern in the Gang of 4 book. I think it's actually the state pattern. And that's just because of the way the pattern typically gets used. So we're going to talk about the state pattern. And then we're also going to talk about a couple of other very important patterns. We're going to talk about the singleton pattern. We're going to talk about the reactor pattern. And then we're going to wrap things up by talking about template method and strategy, which are two very important patterns. Strategy is probably one of the most popular and useful Gang of 4 patterns. So we'll cover those. So we have about a half dozen or so more patterns to cover. By the time you're done, you will have been exposed to about half the patterns in the Gang of 4 book in some detail. You will have gotten a chance to implement many of those patterns. There's still more, but the ones we're covering here are really the basic ones. Any questions? OK, so quiz on Wednesday, and make sure you get your other stuff done so we're not late.